Hello everyone, this is the official CAD design of University of Houston Robotics team. Our drilling rig mimics the iconic oil derrick. The structure consists of a derrick seated atop of the table, all constructed out of 2-inch square steel tubing to provide a strong and steady foundation for the drilling operations. The derricks bolted on the top of the drill floor and allow for easy disassembly for transportation. The rig provides the structural support for our 3 HP top drive encased within a motor housing. The drawdown motor located on the drill floor governs the vertical movement of the motor and housing via a series of pulleys. The motor housing is attached to linear rail that guide the movement and allow for more than 30-inch stroke length while also ensuring the center of gravity is directed over the bed. The drilling floor consists of plexiglass to allow for both visibility and protection, and a mock rotary table to provide support for the drill string at the drill floor.
For this section, we'll be discussing our fluid circulation system. Our fluid circulation system typically begins at the surface from the mud pump. Our mud pump for this system is sized to overcome all the pressure losses in the system and have an additional margin of 100 psi. Fluid enters the drill string via the hose connected to the swivel. Our pressure loss computations account for change in area going from the hose into the swivel and down the drill string. Additional pressure loss computations are made within the drill string all the way to the BHA. Pressure drop across the bit is computed based on published formulas, assuming we have two nozzles. Annular pressure losses are computed across the BHA and across the drill string. Prior to the annular pressure loss calculations, using an assumed ROP of 1 feet per hour, and we estimate the volume of cuttings and correct the mud weight. The mud is received at surface based on design at atmospheric pressure. We'd expect that if the mud is to be recirculated, then we may need to have an additional pressure to that. Following these calculations, we try to optimize the system using the pump rates as a variable. From our design, we recommend operating within 3 and 4 gallons per minute. This is in order to minimize the total losses, as these losses can translate to stretches within the system. For the design phase though, for a start, we would be operating at 2 gallons per minute, which requires to use a pump of 0.27 horsepower. The graph on the right illustrates the optimization discussed. In order to maintain that pressure required at 2 gallons per minute, we would be making use of an electronic water pump automatic pressure control switch fitted to the downstream of the pump.
We will be using a push-to-bed BHA to satisfy the directional drilling requirement, which is to trigger up to 30 degrees inclination, 15 degrees azimuth, and 10 inches horizontal lateral displacement. The push-to-bed configuration will include a 10-inch rotary steerable section in the BHA. There are sensors in the upper annular housing and 4 steerable pads in the lower annular housing. This section will be stationary, isolated from the rotary parts by radial bearings. The 4-pad system will push against the wall to provide the required side force to steer the bit. The pads are connected to the snail cam. It will be operated by a stepper motor for motion. The 2.5-inch long stabilizer will act as a fulcrum point. When the pads open against the wall, it will provide a side force and will act on the stabilizer and on the drilling bit to drill directionally.
So for the control systems, we'll be using these sensors to measure key inputs. The IMU will provide azimuth and inclination as well as vibrational data for the BHA. The IR proximity sensor will provide the measured depth or the vertical travel of the motor housing, from which we can derive total vertical depth. The S-beam load cell will measure the tension on the drawstring, which can be used to derive the weight on bit. Lastly, the variable frequency drive will measure the RPM and the torque of the main motor. And this VRF FD also will vary the motor outputs to change the RPM and torque to achieve optimal drilling parameters. As seen in this image, the IMU will be located downhole in the BHA. The S-beam load cell will be placed between the housing and the drawstring cable. The IR proximity sensor, along with an accelerometer used to measure vibration, will be located in the housing with the top drive motor. Additionally, 2 limit switches will be placed on the elevator rails to determine the bounds of the housing's travel. Lastly, the variable frequency drive, along with the sensors for the fluid circulation, will be placed on the rig, not shown in this image. Lastly, we'll be using a National Instruments USB data acquisition device to collect the data, convert it, and transmit it to the host computer, which will be kept off board from the rig on a separate table.